Now we'll talk about mapping the Milky Way, the galaxy of stars that we live in, which also happened through the 19th century. The history of galactic astronomy starts with Galileo, who discovers that the Milky Way is comprised of many stars, just using his small and simple telescope. In other words, the gauze of light that we call the Milky Way, why it's called the Milky Way, is actually made of the unresolved pinpoint light of many stars. This to Galileo gave him a sense of depth, the third dimension, and he recognized, although he could not accurately measure it, that we must live in a vast system of stars, and also that the stars could be very far away. It reinforced his belief in the Copernican system. By the mid-18th century, Immanuel Kant, a philosopher, is theorizing that the galaxy has a planar structure, and making a more audacious speculation that some of the fuzzy objects in the night sky might be other systems of stars like our galaxy, island universes. Charles Messier, in the later part of the 18th century, compiles a catalog of these fuzzy objects, some of which have spiral structure, including the Andromeda galaxy, that's Messier 31. And, as we'll see, William and Carolyn Herschel conduct the first all-sky survey cataloging 5,000 nebulae and resolving some of them into individual stars. William Parsons, Lord Rosse, using a 72-inch telescope, classifies the nebulae into featureless ellipticals and galaxies with a whirlpool-like structure, spiral galaxies like our own. There's an important idea that comes up in this period of time, posed by William Stuckey, but thought of originally by Olbers. It's called Olbers' paradox, and it was an item of great discussion amongst the astronomers of the time, Edwin Halley and Isaac Newton. It stems from this, that the light from any object goes down as the inverse square of the distance. But the surface area at any distance increases as the square of the distance. So the surface area out to a particular distance goes down at the same rate that the flux from any object goes down. And thus each spherical shell contributes the same background light. So, if the universe is infinite and homogeneous, that is not to say different at any distance or direction from us, then a question arises, why is the night sky dark? Newton's infinite universe was also not stable. So let's revisit this idea again using the diagram at the lower left. We can use the analogy of being in a forest of trees. If the forest is infinite, then even if there's no tree near you, logically, if you look in any direction out along the forest, your eyesight or your sight line will eventually hit a tree. Essentially, the perimeter is covered with trees. Taking that into 3 dimensions, we see Olbers' paradox, where even if there's no star near you, in an infinite universe, in any direction you look, eventually you will see a star or intercept a star. And so the sky should be bright at night. And mathematically, since the number of stars in any shell goes up as the rate of each star's light going down, the contribution of light from each successive shell is the same, and it just piles up to be infinite. This is the paradox of Olbers. Newton recognized another issue, that in his infinite universe, this universe was not stable. According to Olbers, it had infinite amount of light, which made no sense. The night sky is dark. But also, it has an infinite amount of gravity, because gravity works the same way. It goes down as the square of the distance, and then there are more and more objects as you go further out, so the total amount of gravity is infinite. Newton did not know how to resolve this issue. In fact, it was not fully resolved until the 20th century. We have sort of here, in these primitive ideas that have real cogency, even at the time, of the beginning of scientific cosmology. It's clear that the distribution of stars in the sky is not uniform. The Milky Way looks like an arc across the sky, and as we've seen, even from the time of Galileo, we know it resolves into individual stars. With better telescopes, such as with William Herschel, some of the nebulae or fuzzy objects in the night sky also resolve into stars. And so we have speculation from theorists with no way really to prove the hypothesis, from Thomas Wright, that the universe is infinite and that there are island universes. This is echoed in Immanuel Kant's Universal Natural History and Theory of the Heavens from the middle of the 18th century. Kant supposed that the universe, or the solar system rather, formed from a rotating cloud. The gravitational collapse of the rotating cloud flattens it to a disk. And so he imagined that an analogous process might flatten a system of stars like the Milky Way. So he applied this same idea in physics to larger scales. And then he speculated that the nebulae seen in the night sky were island universes like the Milky Way. He thought they had no limit in distance and space. He even imagined, as you see in the diagram to the right, that there was a fractal or self-similar distribution of larger numbers of smaller objects, cascading infinitely out into space. This is a quite audacious cosmology for its time. Meanwhile, astronomers were working on another foundational issue. Nobody knew what the distance to any star was over 200 years after the invention of the telescope. The reason, of course, is that the stars are very far away. So if we look at the geometry of the situation, we see what people were hoping to do, which is discover the aberration of starlight. People also didn't know whether the Earth was moving, and this aberration of starlight is the way you find that the Earth is moving. In other words, if the Earth is moving through space, and we use the analogy below of someone walking through a rain, we can see that if we were static, the rain would fall vertically. But if we were moving forward, the rain would appear to fall at an angle. And that difference in angle between vertical and coming towards us is caused by our motion. That's an analogy of rain falling on someone that gives an example of why you have an aberration angle. Of course, in the case of a star and the Earth's motion is a small fraction of the speed of light. So this aberration angle is a small angle, which is why it was so hard to measure. But finally, in 1782, James Bradley discovered the aberration of starlight. And so we have, after a very long time, the proof that the Earth moves around the sun. Interesting that so long after Copernicus, it takes an astronomical measurement of quite a lot of precision to show that the Earth is actually moving. Meanwhile, the distance to the stars was the other major consideration. The first measurements naturally assumed that all stars are the same intrinsic brightness, and so the apparent brightness of a star was a reflection of its distance, light going down as the inverse square. It's traditional in astronomy then and even now to assume what's called a standard candle, to assume that a particular type of object, like a star or a supernova or even an entire galaxy, has the same intrinsic brightness, so that the relative brightness of two of them tells you their relative distance. Now, this is a dangerous assumption because it's an assumption. Newton, for example, used how faint the stars were, the brightest stars, compared to the sun, and the assumption that they're intrinsically the same object, to deduce that the nearest stars must be hundreds of thousands or maybe millions of astronomical units away. But this is a plausibility argument involving a huge assumption, and it's no way a proof of the distance to the stars. Bradley had failed to see parallax, and so he put a limit on the stars that they were further than a few 100,000 astronomical units. The method here can be seen with the example in the diagram. It's the way surveying works. Imagine you're trying to measure the distance to a tree on a far side of a river. You had no access to the tree directly. You could use surveying equipment. You could measure the angle of the tree as seen from two positions on the near riverbank, and knowing the distance between those two measurements give you the baseline, and then the small angle equation gives you the distance to the tree. So this is a simple surveying technique, and now we're applying it to a long, skinny triangle played out in space, where the baseline is measurement of a distance that we know, and the angle is a measurement from two different places at the same time. Now, measuring on opposite sides of the Earth doesn't give you a long enough baseline to measure stellar parallax. And the baseline you have to use now is the Earth's motion around the sun, a much larger baseline, which gives you more leverage to measure this small angle. So you can recognize that this parallax measurement was not even possible until we measured the Earth-Sun distance. But by the 19th century, this had been measured. And so, parallax depended on measuring the apparent angle of a star against a backdrop of more distant stars, how it changed from one position in the Earth's orbit to another, 6 months apart, say. Here we see this shown in a diagram. You make a measurement of a star's position one time and then 6 months apart when the Earth's at the opposite side of its orbit, and a nearby star, the easiest one you can measure a parallax angle for, will appear to move against a backdrop of more distant stars. This is the stellar parallax. This was the thing that was so hard to measure because the angle is so small. The parallax effect, it's foundational to astronomy, so let's look at it one more time. As the Earth travels around the Sun, nearby stars seem to move backwards and forwards, apparently on the plane of the sky relative to distant ones. It's simple geometry in the small angle equation to use the known size of the Earth's orbit and a measurement of that parallax angle to determine the distance to the stars. For reference, an angle of 1 arcsecond parallax angle is a distance of 3 1/4 light years. And this is now abbreviated, parallax of 1 arcsecond, to parsec. So 1 parsec, the angle subtended in parallax by a star at a distance of 3 1/4 light years, is a foundational unit in astronomy. Smaller angles will indicate larger distances. The first measurement of the distance to any star was made by Friedrich Bessel in 1838, again, almost 240 years after the telescope was invented. He measured a parallax angle of 0.3 arcseconds, you can see how small that angle is, for 61 Cygni, and derived a distance of 10 light years. That's 630,000 astronomical units, corresponding to almost 100 trillion kilometers, or 60 trillion miles. So for the first time, we know the prodigious distance to even the nearest stars. Now we consider the incredible siblings of science, William and Caroline Herschel. They are major figures in the history of astronomy, and Caroline Herschel, of course, was an unsung heroine of her time, but she was a full partner in the observations made by her brother. We can look at their biographies here. They were both born in Hanover, Germany, and moved to the United Kingdom. Actually, the Herschels were escaping a brutal, long war, the 30 Years' War, that was roiling Europe at the time. Herschel was initially employed as a music teacher. He was a more than minor composer, and he was a band leader. So his bread and butter was music, not astronomy. Remember, at this time there were no professional astronomers. And it was music that actually led him into math and astronomy. He was appointed the court astronomer to King George III after he'd made his reputation, and by the end of his life was known to be one of the most notable observers in the history of astronomy, and also one of the best telescope builders in the history of astronomy. His sister, Caroline, was born 12 years later, was 12 years younger. Her mother believed women should not be educated, so she had to educate herself at night and read books at night and in secret. In day, she made calculations for William, and at night, she explored the universe herself. She was also a first-rate observer. We call her the First Lady of Astronomy. She was also the first woman to discover a comet and became a pioneer by the end of her life in the study of comets. Their major joint accomplishments include observations that helped double the known size of the universe. They were the first to accurately describe the Milky Way as a disk of stars. They mapped the spiral nebula, showing that many of them are like the Milky Way. They discovered Uranus, the first planet to be discovered since antiquity in 1781, and they discovered binary stars, stars that were held together by mutual gravity in 1802. They also jointly pushed forward the science of building telescopes with a series of beautiful telescopes made out of wood, carved with brass fittings. They're gorgeous if you can ever see modern versions of them, or in a museum, they're actual instruments. They're exquisite works of art. Herschel, with access to much larger apertures than anyone previously, found that many telescopes, many nebulae resolve into stars like the Milky Way. We can see his 40-foot telescope here on the right, an incredible construction being held up by that lattice work of wood, moving angles in the sky and then pivoting on a turntable. He postulated that we would live in such a nebula. In 1785, in his book On the Construction of the Heavens, he attempts the first astronomical statistical survey. At this time, he's only using a 20-foot telescope, and he's counting stars in the plane of the Milky Way. He decides that the number of stars in any given direction gives the extent in that direction. He's assuming that stars are distributed in space and taking their statistical distribution as a measure of extent. Later, he realizes with his larger telescope that he's made a mistake, that this is what's called a selection effect. He's actually looked at stars down to a particular brightness limit, not a volume limit, which is a limit to a specific distance. And this is a fundamental issue of astronomy. Because we're limited in the brightness of things we can see, we don't tend to see all the objects in a particular volume. Herschel attempted to determine the size and the shape of the Milky Way by assuming that all stars have the same intrinsic brightness. It's an assumption he had to make. And by assuming that stars are arranged uniformly throughout the Milky Way, and that he could see to the edge of the system. This is the diagram he produced of the stellar system of which we're a part. You can see he's located us near the center of the system of stars. He couldn't account well for an important effect that we now know to be important, the fact that there's dust between the stars. More dust along the disk causes the distribution of stars to appear to drop off artificially. And in fact, it turns out that objects more than a few thousand light years away are completely obscured by dust, and we can't see them at all. Herschel came up with a model of the universe that he called the grindstone model. He defined the sun as being near the center of a wheel-shaped group of stars, that the Milky Way was flat like a grindstone. He did counting along 683 sight lines. This was an enormous observational effort that took him years and hundreds of nights. He did most of observing in Bath in the southwest part of England. It's not a wonderful place for doing astronomy, so I'm sure he had many cloudy nights. He was persistent, like Tycho Brahe before him. He assumed all stars have the same luminosity, and they could be seen to the edges of the universe. Now at this time, he was considering the galaxy to be the universe, so these were the same things for him, the universe and the galaxy. His accomplishment was to establish the idea of the Milky Way as an autonomous celestial body, and he did extend the boundaries of the known universe much further than anyone had thought, because he had a larger telescope, a better telescope, and he cataloged fainter and so more distant stars. The only real mistake he made was to neglect the effect of dust, which we now know to be important. We can see this in the example. In the diagram above, if we look out of the plane of our galaxy, this flattened disk of stars, we see relatively few stars, and we can see clearly into the depths of space. But if we look in the plane of the galaxy, we see the band called the Milky Way, which arcs over both the northern and southern skies. In the analogy below, it's as if we were in a fog, where it's impossible to see straight ahead through the fog, but we can see up out of the fog to a distant light. This is the dust, the equivalent of the fog, that Herschel did not know existed, and so it led him to underestimate distances and sizes. This is a more modern view of the shape of the Milky Way, showing an edge-on view and a face-on view. We exist about 2/3 of the way out of the center at a distance of 8,000 parsecs, times 3 and a bit, you get light years, so about 27 or 28,000 light years. And the entire system is 50,000 light kiloparsecs across. 50,000 parsecs is about 170,000 light years. If you look down from the top, you see there's a bulge of stars, a central concentration, and a set of spiral arms where we exist in the second spiral arm out from the center. This is a more modern view of the distribution that Herschel was trying to measure for the first time. And here, informed by modern knowledge, and with a fisheye telescope, you can see, taking a picture of the entire sky, we see the Milky Way beautifully with a clear, dark sky. View within the plane of the galaxy, the pileup of stars, the ragged nature is because of the dust, not because stars are absent in those darkened regions. And then looking above or below, we look out of the plane of the galaxy to a sparser distribution of stars. Also, there are motions involved here, and we give a modern view of these motions. The stars in the neighborhood of our sun are moving randomly relative to each other. So we look in a small box that may be a few light years on a side, we might count a few dozen stars moving randomly with respect to us, some towards us, some away from us. We're 28,000 light years away from the center, and the sun and all the stars around us, we're doing a 230 million year orbit of the center of our galaxy. That's the rotation of the disk. In another galaxy far, far away, maybe the geometry and the architecture is a little bit different. Let's see what this looks like with modern data. Here's Hubble Space Telescope data taking us through a nearby region of a galaxy in a fly-through towards the Orion Nebula, which is 1,500 light years away. This is a voyage through our galaxy that was not possible, of course, until we had modern data.
Using volume visualization, we can investigate the three-dimensional structure of the Orion Nebula. This nebula is an enormous cloud of dust and gas that is several light years across and 1,500 light years from Earth. Gas in the cloud glows from the light of 4 hot young stars at the heart of the nebula. Each star is thousands of times brighter than our sun. The center of the nebula is hollowed out by radiation from these central stars. We're passing a cloud called HST-10, known to astronomers from Hubble Space Telescope images. A disk of dust and debris orbits the star. Astronomers believe this marks the birth of a system of planets. Each of these teardrop-shaped clouds is a blanket of gas and dust that surrounds a newborn star. As we pull back and end our journey, we see the nebula from the viewpoint of Earth.
Here are some of the nebulae that were catalogued by Charles Messier. Messier produced a catalog of 110 fuzzy objects, or nebulae. He was a comet hunter, so they were the targets to avoid. Messier objects are a mixture of star formation regions, clusters of stars, planetary nebulae, supernovae, or dying stars, and there are several dozen spiral and elliptical galaxies located very far from the Milky Way. At the time Messier made his catalog, we didn't know physically what many of these objects were, or have any idea of their distances. Messier objects provide a wonderful lineage in astronomy. They were used at the time and objects of interest, pushing the boundaries of the telescopes, and in the modern world, amateur astronomers still look at them. They have Messier competitions for how many Messier objects amateur astronomers can find with their small telescopes in a night. So the Messier catalog has been very important. They're characterized by an M in front of a number, M31, Andromeda, M51, another spiral galaxy, and a number that are familiar to most people. So Herschel was cataloging nebulae, and he investigated them, these fuzzy patches in the sky, and he expanded the list of his contemporary, Charles Messier. He eventually made a catalog of 500 new nebulae and clusters of stars. He identified 2,500 planetary nebulae, which are clouds of gas that surround stars, and over 800 binary stars. These are pairs of stars bound by gravity. So he was a prodigious observer, and he cataloged more of these types of objects than any astronomer before. In 1835, Lord Rosse argued that the nebulae resembled whirlpools, and speculated, as Kant had done as well, that they were spiral nebulae of stars and gas remote from the Milky Way. And this became a major debate through the latter part of the 19th century. Was the Milky Way the entire universe, as Herschel tended to suppose? Or, as some had speculated, were some of these nebulae separate, distant island universes, meaning that the universe was much larger than anyone at the time had imagined? That's the end of this topic.